In this example, we have this particle A, which is traveling along a path, which is given in terms of the polar coordinates of r and theta. R is explicitly said to be equal to 5 theta, where r is in meters and theta is in radians. We know that theta dot is a constant at 2 radians per second, and what we want to do is find the velocity and acceleration vectors for A whenever theta is equal to pi. So we're looking at a position here where A is over here. So one thing that we know is that we need to extend our ER vector from our origin O out toward A. So ER is looking like this. E theta is perpendicular to that, and it's in a direction of increasing theta. Theta is increasing in the counterclockwise sense, as shown here. So E theta would be like this. Okay, so let's use what we know about velocity and acceleration in polar. We know we need to do differentiations of r here in order to get the right terms. So we start out here with the fact that r is equal to 5 theta. And since we're looking at A being when theta is equal to pi, r is equal to 5 pi. R dot. R dot is just the time derivative of r, so that's 5 times theta dot. Theta dot's equal to 2, so this is 5 times 2. So this is equal to 10 meters per second. R double dot, 5 theta to double dot. And since theta double dot itself is a 0, theta dot's a constant, r double dot is a 0. So that's pretty much it. We have V, then we know is equal to r dot ER plus r theta dot E theta. So r dot is equal to 10. R is equal to 5 pi. Theta dot's 2. So this component is equal to 10 pi. A is equal to r double dot minus r theta dot squared, ER, r theta double dot plus 2 r dot theta dot E theta. It's given that theta dot is a constant, so that's a 0. Above we saw, as a result of our differentiation, that r double dot is also equal to a 0. So this is equal to minus 5 pi, that's r. Theta dot was 2, so that's squared. The E theta component, that's 2 times r dot was equal to 10. Theta dot is 2. So that's equal to minus 20 pi. ER plus 40 E theta. So this is in meters per second squared. V meters per second. Okay, so let's make a sketch of this just to see if it makes sense. The V has a positive ER component of 10. It has a positive E theta component of 10 pi, so the E theta is larger than the ER component by about a factor of 3, so we'll make V look like this. We have that for A, we see that The radial component, ER component, is a minus. It's a minus 20 pi. E theta component is a plus 40. So it's going to be something like this. Not sure exactly what angle it is, but if you draw an accurate picture, you'll get the right representation there between V and A. So this was a fairly straightforward application of their polar velocity and acceleration equations. Differentiation wasn't too bad. The equation for R in terms of theta was simple enough. We didn't have to worry about product rules of differentiation or chain rules or anything as that. We simply did the differentiation for R and plugged in the numbers for the expressions there for V and A.